inauguration of our new president, Joe Biden, and Vice President Kamala Harris. Very special day for us. Nice to see you all around the world. And I'm going to be talking today about geometry. Why is geometry so important? I will talk for a little bit on camera here, and then I'm going to switch my camera to an overhead camera because rather than the usual PowerPoint, I'm going to actually demonstrate with some materials today. And we can come back on camera at the end for some questions. But please put in your questions in chat when you have them. So, why is geometry so important? Well, for one reason, it's the most ancient science. It's certainly one of the most ancient sciences, along with astronomy. No matter what civilization you trace back, you'll find geometry there as one of the most ancient ways that people have used in order to try and find order and meaning in the cosmos. And the word geometry itself means the measurement of the earth. Ge is the earth, and metron is to measure. Geometers measure the earth. And geometry was systematized really by the ancient Greeks, based on information from Egypt and elsewhere. They took the work of the Egyptians and others and they systematized it. And Euclid of Alexandria wrote the most famous, what is supposed to be the second most read book in history, they say, Euclid's Elements. And many, many figures throughout history, Galileo, Kepler, Abraham Lincoln himself, Albert Einstein, have all read Euclid's Elements as a way to train the mind to think well, to think logically, and to train and develop the mind. And Euclidean geometry is the geometry that we offer to the reasoning minds of our elementary aged children. Now, Maria Montessori, her approach to geometry was really to see how geometry could serve child development. That's what she was interested in. She was interested in the overall development of children and looking at geometry from the point of view of how that would serve total development. She called her book on geometry, I have it here, Psychogeometry. It was published together with a companion volume called Psychoarithmetic. And these volumes, she says, were based on 20 years of experiment with children, following their psychology. Now, what does that mean? That means, for her, following their interests. What were they interested in? What kinds of discoveries did they make? How did they work with these materials? How did they respond? What seemed appropriate for different age levels? What evoked their concentration, their repetition of activity? What encouraged their self-discipline and their self-control? And what particular materials were so interesting to them that they would continue to make an effort and push themselves even further? So, for the young child, the child under age 6 or 6/7, we offer a sensorial experience of geometry as part of their total sensorial experience at that stage of development. Geometry is given as a key to the world. And it's given in such a way that the children touch, they feel, they trace, and they experience the geometric figures, the geometric shapes in a very, very sensorial way. It's a very concrete approach. I'm going to talk about plane figures today, two-dimensional figures, but of course there are also three-dimensional figures that are explored. We don't have time to go into everything in this short space of time. But this exploration of geometry, or the keys to geometry, to the world of geometry, for the child at the age of 6, is accompanied, of course, by the nomenclature, what we call the nomenclature, or the vocabulary of these geometric figures. because of Montessori's great discovery of the great sensitive period for language development at this age, and the fact that these children are such incredible word lovers. They want the names of everything. They desire the names of everything. And so we have a very systematic approach in not only giving the figures of the basics of Euclidean geometry as keys to the world, but also giving their nomenclature, their vocabulary at this age. So I'm going to switch my camera so I can show you some of the materials that we're talking about. So bear with me for a moment. Here we go. Okay. And you'll let me know, Courtney, if for any reason you can't hear me.
For sure. Yes.
No. So, can you see that okay? Yes?
We can.
Good. So we begin with the young child, with the 3 to 6 year old, by giving these three fundamental figures of geometry. The triangle, which is an equilateral triangle, the square, and the circle. Now, I'll apologize from the beginning for the overhead camera tends to slightly distort figures. So we elongate them. So I know this looks like a rectangle, and this looks more like an oval, and this maybe looks like an isosceles triangle. But I will name things for you so that you realize what we're giving. So the children are given the three most perfect shapes of geometry: the equilateral triangle, the square, which is the most perfect of the quadrilaterals, and of course the circle, which is the most perfect of the curved figures. And these are explored sensorially, and their names are given, of course: triangle, square, and circle. These are the three fundamental figures of geometry from which everything else is derived. And then the children go on to explore further in a systematic way those various groupings. For instance, the children would explore all the different kinds of triangles sensorially here. And there I'll add one from what I already presented. And there are actually, in addition to the one on the first tray, there are 6 more triangles. We call them the 7 triangles of reality. There are 7 kinds of triangles which all can be named. And so that experience of naming these different triangles, of exploring them sensorially, is part of the experience of our 3 to 6 year old children. Likewise, the exploration of the square and of the circle are taken further. There are further trays in our geometric cabinet for the different kinds of quadrilaterals, and there are trays for the different kinds of circles. And there are trays for the other kinds of polygons. These are the first 2 polygons, the triangle and the square. And then there are trays that explore all the other kinds of regular polygons. And of course, the triangle being in a sense, the ultimate polygon, the perfect polygon, a polygon with an infinite number of sides. And then there are trays with for the other kinds of curved figures. So the 3 to 6 year old is exploring the different plane figures in geometry, also connecting them to the solid figures in geometry, and beginning to observe these particular shapes in their world, in their home, in their classroom, outside their classroom, in architecture that they see, in nature, in leaves and flowers, in plants, in animals, in the mineral kingdom, everywhere. So this particular nomenclature and this experience is one of the essential keys to the world that we give to 3 to 6 year olds. the children often experience then a further exploration of the triangle with materials called the constructive triangles. There are several boxes that have various triangles in them that can be used to construct other figures. The reason for introducing the triangle is one of those essential constructors. Montessori calls it the great constructor, one of the essential constructors of other figures. I've taken one of the boxes. This is a hexagonal box. It's a regular hexagon, although it might not necessarily look like that with the camera, but it is a regular hexagon. And I have a selection of the triangles that are in this box just to show you something, give you an idea of the kind of exploration that the children can have with this box. So here's an equilateral triangle. This is an equilateral triangle, not an isosceles triangle, the box. I'll place it over here. And here are some other isosceles triangles that we can build together along the black lines like this. See that? We can connect them along their black lines. And when we connect along the black lines, the children experience that they create with the triangle a new figure. They create a rhombus. So we have another pair that we can connect along the black lines, creating another rhombus. We have a third pair in this box that can be connected along these black lines, creating another rhombus. And this is something that the children under the age of 6 can do. They can take out these triangles and construct with them. So we're seeing the triangles here used to construct 3 rhombi. If we place those 3 rhombi together, we've created a regular hexagon, 6-sided shape, 1, 2, 3, 4, 5, 6. They've had, of course, an experience of the hexagon as one solid shape, not divided already, and they have the nomenclature of hexagon. But here they can discover that the hexagon is composed of 3 rhombi, 1, 2, 3 rhombi. Or you could think of it, it's also composed of 6 isosceles triangles. But they might have even a further nomenclature. It's 6 obtuse-angled isosceles triangles. And the children at the age of 3 to 6 are very capable of acquiring all of that nomenclature. So let's place our hexagon over here to the side for a moment. And let's take out some other material from our box. What do we have here? We have a number of equilateral triangles, smaller equilateral triangles. And if we join these equilateral triangles that I'm taking out along the black lines here, join them along the black lines, we've created what looks like another hexagon. See that? 1, 2, 3, 4, 5, 6, yes. Another hexagon. If I divide it this way, I've created 3 rhombi. Remember when I divided this one, I created 3 rhombi? I wonder if a rhombus from this hexagon and a rhombus from this hexagon are actually the same size. We could compare by placing this one on top of this one like this. Look, they're exactly the same size. Now for the younger children, this can be a very sensorial discovery. Just discovering that they're the same size, they take up the same amount of space. When the children move on to elementary, there's a step up to looking at these and saying that they're actually congruent. They're congruent figures. They take up they have the same shape, they're both rhombi, they take up the same amount of space. And a further step that the elementary children can take is if we take one of the triangles from this rhombus and one of the triangles from this rhombus, we've taken half of each rhombus. This is half of the gray rhombus, and this red triangle is half of the red rhombus. They actually take up the same amount of space. We call them equivalent figures. They're equivalent. They're not the same. They're not the same shape, but they're actually equal because they're half. So this is a reasoning step for the elementary child. So the second grade children who have developed this interest in geometry and this background knowledge of geometry and the language of the discipline, knowing the names of these particular shapes and having some sensorial experience about how they're constructed, then have an additional interest now to go on and reason about these figures, about how they're constructed and how they're put together and how they're actually created. It's a more analytical work, and there's a logic to it. Here you can see that there's the direct sensorial exploration, for example, of these two rhombi, and see that they take up the same amount of space. But then there's a leap into some level of abstraction in thinking, well, if I was to take half of each one of these, they would be actually equivalent. Although they're not the same shape, they actually take up the same amount of space. Of course, this is a preparation, this is a distant preparation for the idea of area. But these particular figures, if one wanted to prove it, could be traced and could be cut in such a way that one could actually prove it sensorially in a very concrete way if one wished. Something further that could be done here, or discovered in this box, and this is just a selection of possible discoveries that children could make, is that children might discover that this particular larger equilateral triangle could fit right in there. That we could actually remove this central triangle, and we could replace it with this yellow triangle. Isn't that interesting? So that can be, of course, a completely sensorial exploration. That's interesting. We have a larger equilateral triangle in the box, which is actually the same size as this triangle, which we could replace it with, and still have our hexagon. But on a next level, on a reasoning level, moving into the elementary, the children could look at this, and they could extrapolate that this yellow triangle is actually half of the hexagon. Because they could take these particular figures, joining them not on the black lines now, but creatively exploring in another way, they could prove that that hexagon was made up of two larger equilateral triangles, each of which were congruent with this yellow triangle. Therefore, we could say that the yellow triangle, the yellow equilateral triangle, was half of our regular hexagon. So that's just an example of some of the possible discoveries that the children can make with that particular device. I want to give you a sense of early, more sensorial discoveries, and also connection to later, more reasoned discovery of the 6 to 12-year-old, who really wants to discover the formula, discover the rule, discover the theorem, and be able to articulate it where that is an actual fact, an end point of the process rather than the beginning of the process. And that's how we approach it. The rule or the theorem or the formula is a point of arrival for us in our work, not a point of departure. So here's an example with some of the other materials. These are metal inset materials that we use. This is actually a square, although it might not look like it. And here we have a circle. Okay. Now, as we explore these, we can discover that the circle can fit inside the square perfectly, inside the square. This circle is circumscribed by this larger square. Now, this is a language that the children can acquire. Circumscribed, inscribed, in order to be able to discover it. Not to say we can say it fits inside perfectly, yes, but this is called a square that circumscribes a circle. We could also find, if we explore our materials, that perhaps we have a square that could fit perfectly inside this circle. So this square is inscribed in our circle. So we have a square inscribed in the circle, and we have the circle in turn inscribed in the larger square, or we could say circumscribed. Square is circumscribed in the circle. Now let's explore a little farther. Let's see if we can place our square here inside our other square. Look at that. I wonder if we have any other materials in our divided squares that we might be able to use to fill in these triangles here. Let's go exploring and see if we have. And so the children go exploring, and they find, sure enough, that they have some more smaller right-angled isosceles triangles that can fit in here. Let's remove this square. Let's see if we can complete the square using some more of these right-angled isosceles triangles. Look at that. We have completed the square. So this larger undivided square is congruent with this square. Let's place this central square back into our circle. Aha. We can see that this square is composed of 4 of these little right-angled triangles. And our larger square is actually composed of these 4 that we placed here, plus the other 4, the 8. So this square, which is congruent with this square, is actually half of the larger square. Now, if the children are familiar with fractions, these can be named as eighths, the ones that we just used. You can see this as I'm placing them back here. It can be named as eighths, but even that is not even necessary at this point in order to explore the congruence that I'm speaking of. So we can say, ultimately, that this smaller square that is inscribed in the circle with obviously the word square and what a square really is. They would need to be familiar with the idea of a right angle triangle, understanding what a right angle is and that this is a right angle triangle. And also have the word hypotenuse for the side that's opposite the right angle. That would be a prerequisite to have that particular vocabulary, because then we can talk about it in an intelligent way. So one of the things that Pythagoras discovered in ancient times was that if you built a square on the hypotenuse of a right angle triangle, that it was equal to the sum of the squares built on the other 2 sides of the right angle triangle. Now, we can see that it would be hard for us to place these squares in here. It's not going to happen too easily, these 2, the blue and the yellow square, into a red square. So what we've done is we've taken these squares and we have divided them along their diagonals. So we've divided the blue square along its diagonal into 2 right angle triangles. We've done the same with our yellow square. And we've taken our red square and we have divided it. I'll just move it slightly here so you can see. We've divided it along its 2 diagonals into a number of right angle triangles also. Now, I won't take the time to do this right now, but it's just show one. We would need to prove that the divided squares are actually congruent to the undivided squares. So one would move it across like this and prove that they're congruent. Yes, they're congruent. They're congruent. And we would do that with the blue and also with the red. So that allows us to use this particular these particular divided squares to see if we can prove that what Pythagoras was saying was true. Okay? So let's remove these triangles here from our red square. And let's move over the blue square. Various ways we can do it. Let's move over the yellow square. Now look, the 2 squares fit exactly into the red square. Let's see if we can place the red square into the 2 other squares. Yes, we can. So we've proved in a very sensorial way that the square built on the hypotenuse is equal to the sum of the squares built on the other 2 sides. Now, of course, this can be taken a lot farther than this. One can explore this also arithmetically. So here's an example of the arithmetic demonstration of the theorem of Pythagoras. So here we have it's a slightly different orientation here. So the right angle is here. There's actually a scalene right angle triangle, whereas the previous one was an isosceles right angle triangle, but they were both right angle triangles. So the hypotenuse is actually here on the bottom because it's opposite the right angle. So here we have the square built on the hypotenuse, this large red square. And here we have the squares built on the other two sides, a blue square and a yellow square. Okay? And they're all divided into smaller little squares. All of these squares, they're divided. And so the children can explore to move the red square into the other two squares, and to move the yellow and blue square into the red square. And you can see here it's possible. This is just one possible way that the children can do it. These materials are what we call them developmental materials, because they're not just for demonstration, they're for the children to continue to explore in different ways. From this, the children can begin to see that the square of 3, which this is, plus the square of 4 is equal to the square of 5. 3 squared is 9. 4 squared is 16. 5 squared is 25. 9 plus 16, 25. That can be written out. Of course, the children have already experienced in their arithmetic materials, they've already experienced a 3 square, and a 4 square, and a 5 square in their counting of the short chains, what we call the square chains. Where the square of 3, I'd be quite familiar that the square of 3 is 9, and the square of 4 is 16, and the square of 5 is 25. And here you see very much the association of the triangle and the square, which the children can explore. The terminology of base, height, perpendicular height, it's an easy step move into the formula with these particular materials. So geometry is really a wonderful way of developing the logical mind of the child, and a wonderful way of extending the imagination, the creative imagination of children, which is so active at the elementary age. And if they have the basis, I'm just changing my camera here. If they have the basis of knowledge of the geometric figures, the sensorial foundation, and they have the vocabulary, there's so much that they can explore, that they can learn to express in an articulate way at the elementary level with these materials. They can derive theorems, they can discover certain theorems for themselves, they can learn how to speak through them, they can make intelligible connections with arithmetic all the time, and also with algebra. Maybe I'll give a quick I'll give a quick demonstration, sort of algebraically. Let's see if I have time to do that. Now, I'll just go back to the camera for a minute just to give an idea of an algebraic connection here. Okay, take this particular plate. In this particular plate here we have a triangle, equilateral triangle, which is divided in a particular way. It's divided into a trapezoid or trapezium, depending on your part of the world that you're in, trapezium, and two smaller scalene right-angled triangles. Okay? This would be the base of the triangle, and here would be the perpendicular height of the triangle. Now let's see if we can transform this triangle into a rectangle. Yes, we have transformed this triangle into an equivalent rectangle. So the equilateral triangle is equivalent to this rectangle. Now that's a very sensorial exploration, very simple. As a next level, we can look at the relationship of the different lines. If one has explored, as I was speaking about earlier, if one has explored that the area of a rectangle is the base times the height, call that B for base, and H for height. Okay, we can look at the triangle and you can say, okay, the base of the rectangle, what is that in the triangle? It's the base, also the base of the triangle. And the height of the triangle, which we can see right there. Okay? What is that in the rectangle? It's half the height of the triangle. It's the height over 2. But the height of the rectangle is half the height of the triangle. So, from that exploration, we can write out the formula that the area of the triangle is equal to the base times the height divided by 2. And that's a discovery that the children can make with this sequenced approach of really exploring sensorially, making discoveries, articulating what has been done, using the language of the discipline, and then taking it a step further to say, okay, what have we actually done here? And rather than naming lines with arithmetical numbers, as we did with the yellow material, naming them here with letters, moving into an algebraic expression becomes quite natural and an easy step for the children with this particular approach. All right, I'll stop there, and we can take some questions.
Great. Jerry, thank you so much. There have been some questions, so I'm going to start to ask those. I will just read them from the question section. I'm not going to announce the asker unless you would like to have a discussion with them. You can just let me know. But the first question is, would a child who has not had primary training be able to do the type of work that you showed in the elementary classroom? And the person is specifically interested in a child around the age of 7.
Well, what one has to do is one has to give the children an experience of the material and the nomenclature that one would have had in the primary classroom. So some of that can be done as a prerequisite, and some might be done, in the context of the work. They won't have the same sensorial experience or the same absorption of the material that they would have had during the phase of the absorbent mind in the first plane. But I've certainly had children come in at the elementary level, both at age 7 and later, who haven't had that early experience, and they can still dive into this material and really use it in an exploratory way, in an analytical way, which is suitable for the elementary child. But you just have to be aware of the fact that you maybe have to give this, some of these experiences a little bit more didactically and maybe more quickly than one would have given them at an earlier age, so that they have the background and enough background so that it really becomes an exploration, and there's a possibility for some guided discovery, rather than you just saying, well, as I put the material, well, here's the material where you can derive the formula for the area of a triangle. Boom, boom, boom. I mean, certainly you could demonstrate it like that, but that's not what we're looking for.
Great answer, Jerry. Another question is, what would you propose to be some of the most important prerequisites or preparatory materials in the Children's House for this type of elementary work?
The geometric cabinet and all of the nomenclature of the geometric cabinet, the sensorial exploration of the geometric cabinet, the cards that go with the geometric cabinet, the language, of course, and then taking those keys and applying them to the environment, to the indoor environment, to the outdoor environment, to observing one's world. The geometric solids are very important, and one connects the two-dimensional geometric cabinet to the three-dimensional geometric solids in terms of their faces. So again, exploring with those, seeing how they connect to each other. Oh, this square-based pyramid can fit on top of this square-based prism, and so on and so forth, to various connections. This pyramid has a circular face which can sit on top of this circular face of this cylinder. Oh, a cylinder has two circular faces, etc., and so on. So there's so many early discoveries that can be made and then talked about, putting the sensorial experience together with the language. The constructive triangles are very, very important, as you may have gathered from me showing them here. Exploration of those triangles and their nomenclature are extremely important. The superimposed geometric figures are very, very important. And of course, there's all the geometry that comes through other materials. Let's say, the bead cabinet, there's a tremendous amount of geometry in the bead cabinet. We even have, we have a circle for the noun symbol, and we have a circle for the verb symbol, and a red circle, and a black equilateral triangle for the noun symbol. Okay, so when we introduce the functions of those words, without the names, but we introduce their functions, and we give those symbols early on. So we have many, many symbols. Tracing the metal insets. The metal insets are geometric figures. So the metal insets are used for preparing the hand for writing, but they're also being used for geometric design. So the early geometric design with the 3 to 6 metal insets is a very important prerequisite to design with the other insets that the children come upon when they come into elementary. So those would be some of the major experiences. But all our sensorial materials, Pick Tower and the broad stair and so on, are all preparations for the work of the elementary, because they're giving key experiences of the world of geometry, and a sense of the relationships between things. I mean, there are relationships between the Pick Tower and the broad stair, or the brown stair, that can be discovered, and so on.
Is geometry still important for the adolescent, and why?
Oh boy, absolutely. Very important for the adolescent. And again, it's a wonderful activity to stretch the mind. But it's also something beautiful. I mean, geometry has been used from time immemorial by human beings to make sense of the world, to order the chaos of the world, and to create harmony. I mean, in our philosophical traditions, our religious traditions, our art, one finds the harmony and the beauty and the order of geometry. That's very satisfying to the incredible creativity of the adolescent mind. As you know, adolescents are a very second birth of incredible creativity. So geometric design using compass and straight edge, 3D design with geometry. I mean, there are a lot of programs now that can be done on the computer with geometry, some excellent ones. But I would always recommend doing some, geometric construction with compass and straight edge first, and really discovering the potentials. I mean, there are some extraordinary things that the children can do. You can use compass and straight edge. Adolescents can do this to create, a two-dimensional representation of a three-dimensional icosahedron, for example. That can be done with compass and straight edge and other similar things. That could be a next step for adolescents. So I think geometry is a very important discipline that can be continued. And then all the practical aspects. There are so many practical aspects of geometry. Whether it's learning to do triangulation out in a field, or whether it's in the wood shop, using tools to cut at right angles or 45-degree angles and so on. I mean, you just find it everywhere. So that practical application of the occupations is also something that should be connected to what the children are studying. How does somebody create, if you're building a wall, how does somebody create a wall at an exact right angle? There are intriguing little ways that masons do that, which are very ancient and go all the way back to the ancient Egyptians. So those are interesting things to explore.
Right.
So I could go on.
No, I know it's great. There's a couple of questions that I'm going to leave to the end, but how does geometry relate to dance, visual arts, including painting and sculpture, architecture?
Well, that's a huge question.
How does love of? Yes.
How does love? Well, I think yes. That's a good question. I love it. I mean, obviously there are so many connections to music. I mean, music is very geometrical. I mean, to art. There are so many artists that use all kinds of geometry in their work. Of course, there's perspective. There's the use of perspective, which is geometry, and architecture. Naturally, there's geometry everywhere in architecture. But I think a love of geometry and an understanding of geometry and of the history of geometry can only enhance one's appreciation of all those different humanities, or sciences. Because one takes a look at a building like the Alhambra or the Pharaohs of Alexandria, or in a completely different way, or one walks into a building and looks at a ceiling like in the Capitol building or the tiled floor with a different eye, because one has had that experience. It's just it goes without saying. Just as we could, if we listen to a piece of music by Mozart and we have some musical training in order to identify. If you like a certain geometry or pattern in the music, it can only enhance our experience. So I would say, yes, a love of geometry. I mean, children love geometric design and coloring geometric, creating geometric designs, coloring them and so on. Very, very good concentrated work. It's work which really continues to develop concentration throughout the years, throughout the elementary into the adolescent years, no doubt about it.
Lots of questions, they're great. And one of the questions, there's a couple about books that you could recommend for parents, but also even the elementary child, books that introduce the historical aspects of geometry. And then along that line, I'm going to add in the question about, in Ireland, is there a place to get good quality or good price or fair price Montessori materials? Three questions in one.
Okay, give me one at a time because I have short
time. Sure. Books for adults, for parents, on the subject of geometry and.
Well, we could post something. I mean, there are so many books. There are so many books for parents. There's one called Euclid's Window, which is interesting. I don't know, I can't remember the author right now, but I have it here. Euclid's Window by Leonard Mlodinow, Mlodinow. Euclid's Window by Leonard. That's a good one for parents to read. But there are so many great books for children. Like one that I love is The Librarian Who Measured the Earth, which is about the ancient librarian of Alexandria in Egypt from 2,000 years ago, who of course was a geometer and an astronomer and figured out how to measure the circumference of the Earth. Great story. And there's a children's book about that, and there's so many children's books like that. So we could post a short list of books that for children to read or for parents to read to their children. What was the next question?
The exploration of the metal insets that you did with the inscribing and circumscribing of the square, they've commented it's lovely. It was lovely, and is that usually done in the elementary while doing congruent, similarity, and equivalence?
Not necessarily. It's not necessarily part of all the training courses. But of course, everything that is possible with this material is not presented or could not possibly be presented on the training courses. But I encourage you, if you're a trained elementary person, I encourage you to explore the material in this fashion yourself, and to explore it with the children, because there are many other discoveries that can be made. Some of this you will see referenced in Psychogeometry by Maria Montessori, and I just encourage you to explore. Part of the reason why I showed those today was because they're not generally shown, so I want there to be something interesting for people who are already trained that they might not have seen already.
Great. A question, there's so many, I can't wait to share all these comments with you, Jerry. Everyone's loving this presentation. Whoops, just lost it, pardon me. There's a question about what are some of the ways that the CASA Guide can foster children seeing geometry in the real world, besides what you've perhaps mentioned already?
Well, one of the ways I think about it is in nature. Right away, is looking at the shapes of leaves. Leaves are very geometric. Many leaves are very geometrical shapes and are even named. There are names that are connected to their shapes, so that's very interesting. The shapes of stems, flowers. flowers have all kinds of interesting geometry in them. One can find geometry in the animal kingdom, particularly among the invertebrates, but also elsewhere. So, using a hand lens or a simple microscope, one can look at pond water, and one can see little protistums that have interesting geometric shapes. One looks at snowflakes, one and so on. It's just one can have crystals, different crystals and minerals in the classroom, or look at them in books, and identify different. So there's so much in the world of nature. The other is in architecture. And so, a simple little field trip, sometimes even walking a neighborhood. And like the neighborhood that we're in here in Hartford, and it's close to West Hartford, there are houses with many different kinds of architecture, Italianate and federal architecture and colonial and neo-colonial and so on. So all kinds of interesting architecture, and with their particular names, and all based around circles and squares and triangles and so on and so forth. And so one can introduce the children to a little more of the terms of architecture, and like the Greek columns and so on, and then go find it in the neighborhood. Or children who are particularly interested in the elementary can have it going out into the center of their city and explore, looking for geometry in nature, and particularly in famous buildings and so on. So I definitely think I've done that here myself with workshops, people who we've gone out exploring the neighborhood and finding the geometry in the world around us. There's no end to it. So those would be the two main areas that I would think of.
Wonderful, Jerry. There's no more questions at the moment, and there's just a lot of gratitude and that they're sharing, and we will definitely share this with you. There's been an education of people that have never understood the Pythagorean theorem before, so I do.
I think you're very welcome. It's a very short time to talk a lot, and there's an awful lot to say, but I hope you've had some taste of our approach to geometry, and why geometry is tremendously important for child development, and for developing the potential of each child, and also in developing the child in relation to the world around him or her, because it is tremendously important. So look farther. We'll put up a list of some books for parents and for children, both young children under 6 and over 6. I can't promise how quickly that will be up, but we will do that. At least we'll put up a short list for you. And thank you, everybody.
Sure. Thank you. And before we go tonight, I just want to thank again Leslie Seibel with Cap Ed and the University of Hartford, and just want to put out there that this is sponsored in part for the program at the University of Hartford, the Montessori Studies program, particularly the Master's in Education with the Montessori concentration. So if you're interested in finding out more, please, you'll get a follow-up email from us with the book list and additional information on how you can access this webinar and share it with your friends. And you can certainly ask questions about any of the degree programs that we offer in partnership. Thank you so much, and have a wonderful evening.
Thank you, everybody.
Good night.
Good night.